July 21st, 2023. A routine set of commands leaves Earth, aimed at a spacecraft more than 12 billion miles away. Nothing about the upload looks unusual. It's the kind of software update engineers have sent 1,000 times before. But this time, something goes wrong. The command tilts Voyager 2's antenna 2 degrees off target, just 2 degrees, and in that instant, humanity's most distant working machine stops talking to us. Not degraded, not glitching, silent. To understand why that silence mattered so much, you have to understand what Voyager 2 actually is. It isn't just an old satellite drifting on momentum. It's a fully operational science platform, still running instruments, still collecting real data, in a region of space where nothing else humanity has ever built currently exists. When it stopped talking, it wasn't a nostalgia problem. It was an active loss of the only working outpost we have in that part of the universe. For the next 2 weeks, the people who built and flew this spacecraft for nearly half a century have no way of knowing if it's still alive. And what happens next, both the frantic attempt to reach it and what scientists have pieced together in the years since, is stranger and more revealing than most people realize. This isn't a story about a spacecraft going quiet. It's a story about what almost ended one of the greatest scientific missions in human history, and what we've learned since that moment that's rewriting our understanding of the outer solar system. Let's go back to the beginning. Voyager 2 launched on August 20th, 1977, 16 days before its twin Voyager 1. Both spacecraft were built to take advantage of a planetary alignment that happens roughly once every 175 years, one that let a single mission use the gravity of each outer planet to slingshot toward the next. Voyager 1 took the faster route, past Jupiter and Saturn, then out of the solar system entirely. Voyager 2 took the long road. It's still the only spacecraft in history to have visited all 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. At Jupiter, in July 1979, Voyager 2 passed within roughly 400,000 miles of the planet, sending back around 17,000 new images and capturing evidence of active volcanoes on the moon Io, the first confirmed anywhere in the solar system besides Earth. It also caught the Great Red Spot itself in the middle of changing shape and color between the 2 Voyager flybys, something the earlier Pioneer missions hadn't even detected as possible. At Saturn, it revealed a ring system built not from a handful of broadbands, but from thousands of individual, tightly packed ringlets, a level of structural complexity nobody had modeled before Voyager actually looked closely. Then, in January 1986, it became the only spacecraft ever to fly past Uranus, discovering 10 new moons and 2 new rings in a single encounter. Moons with names like Puck, Portia, Cressida, and Ophelia, continuing the mission's tradition of naming discoveries after Shakespearean characters. 3 years later, in 1989, it did it again at Neptune, finding 5 new moons, 4 rings, and the strange, storm-like feature known as the Great Dark Spot, a rotating atmospheric system roughly the size of Earth itself. To make the Neptune flyby work at all, mission planners had to redirect Voyager 2 out of the plane of the solar system entirely, a decision that ended any possibility of visiting another planet, but opened the door to everything that came after. Both spacecraft also carry something that has nothing to do with planetary science at all: the Golden Record, a gold-plated copper disc loaded with sounds and images of Earth, greetings in dozens of languages, and a cartridge and needle to play it, meant as a message in case either spacecraft is ever found by someone or something else. It's easy to forget that detail exists at all, bolted to the side of a machine that spent nearly 50 years doing hard physics in the dark. But it's still out there, attached to a spacecraft that very nearly stopped talking to its own creators in the summer of 2023. By the time Voyager 2 finished its planetary tour, it had already rewritten multiple textbooks. And it wasn't done. In November 2018, it crossed the Heliopause, the boundary where the sun's solar wind gives way to the pressure of interstellar space, becoming only the second human-made object, after Voyager 1, to leave the bubble the sun carves out around our solar system. Both spacecraft are still out there today, moving through space no other spacecraft has reached, using instruments built with 1970s technology to send back data that machines from the 21st century still can't replicate, because nothing else is out there yet. That interstellar data has already produced findings nobody expected. After Voyager 1 crossed the Heliopause in 2012, its plasma wave instrument, the same type of instrument still running on Voyager 2, picked up something researchers later described as a faint, persistent hum, a low, continuous oscillation in the thin plasma of interstellar space, distinct from the occasional bursts caused by solar eruptions reaching that far out. It wasn't a signal in the sense of a message. It was closer to background noise, the ambient vibration of the interstellar medium itself, but it told scientists something concrete, that the density of plasma in interstellar space is higher and more consistently active than models had predicted before either spacecraft actually got there. That single detail matters more than it sounds like it should, because it's one of the only direct measurements we have of what the space beyond our solar system is actually made of and how it behaves, And it only exists because these two 1970s machines are still transmitting. Before Voyager 1 and Voyager 2 actually crossed into interstellar space, most models treated the transition as something gradual, a slow fade from the sun's influence into the emptiness of the galaxy with no clear edge. What both spacecraft found instead was a real boundary, crossed over the span of about 2 days rather than years, with solar wind particles dropping off and galactic cosmic rays surging almost immediately after. The heliosphere, in other words, isn't a fuzzy border. It's closer to a membrane, thinner and more sharply defined than almost anyone expected, and the interstellar magnetic field pressing against it from the outside turned out to be stronger than existing models had assumed too, compressing the sun's bubble more tightly than scientists had planned for. None of that was knowable from Earth. It only became knowable because two spacecraft launched in 1977 happened to still be working when they reached that boundary, decades later in the 2010s. Which is what makes July 2023 so unsettling. Because for 2 weeks, it looked like it might all end on a technicality, a routine command, a 2-degree error, and silence. Here's what actually happened, step by step, based on NASA's own mission updates from the Jet Propulsion Laboratory. On July 21st, a series of planned commands were sent to Voyager 2 as part of normal operations. One of those commands inadvertently caused the spacecraft's high-gain antenna, the dish that sends and receives all of its data, to tilt 2 degrees away from Earth. That's it. 2 degrees at a distance of over 12. 3 billion miles, that small an offset was enough to break the link entirely. Voyager 2 could no longer receive commands, and its data was no longer reaching the Deep Space Network, the system of giant dish antennas NASA uses to talk to spacecraft across the solar system. Think about the scale of what that means. A one-way radio signal from Earth takes about 5 hours to reach Voyager 2, so even a perfect, immediate fix would take more than a day and a half round trip just to confirm it worked. And now the spacecraft wasn't pointed at Earth at all. Every future command, if they could even send one, would have to travel that same 5 hours through space and hit a target that wasn't listening. NASA's engineers had one scheduled backup. Voyager 2 is programmed to automatically reset its own orientation several times a year, precisely so that if anything nudges its antenna off course, it can correct itself and repoint toward Earth without needing outside help. But that reset wasn't scheduled to happen until October 15th, nearly 3 months away. For those 3 months, if nothing else worked, Voyager 2 would simply keep flying deeper into interstellar space, deaf and mute, its onboard science instruments still running, still collecting data on the plasma and magnetic fields of interstellar space, but with nowhere to send any of it and no way for anyone on Earth to reach back. Losing 3 months of contact with a 46-year-old spacecraft that's already operating past its design life is not a small risk. Every additional day of silence is a day where something else could go wrong, with no way to intervene, no way to run a health check, no way to even confirm the spacecraft was still functioning at all. A micrometeoroid strike, a component failure, a software fault of any kind, a sudden thermal swing in a system already operating decades past its original design specifications. Any of it could happen during those 3 months, with zero ability for engineers on Earth to detect it, diagnose it, or respond in time to matter. The mission team wasn't willing to simply wait it out, but forcing an early fix carried its own risk, sending an unusually powerful, non-standard command to a decades-old spacecraft, one whose exact receiver sensitivity after 46 years in the radiation and temperature extremes of deep space was itself something of an unknown, meant there was a real chance the command could be misread, ignored, or simply too faint to register at all, given how far off axis the antenna was actually pointed. If the high-power shout failed, and worse, if it somehow triggered an unexpected response from the spacecraft's fault protection software, the team could have been left worse off than if they'd simply waited for October. That's the trade-off that made the decision genuinely difficult for the mission team. Not just tense, not just a matter of nerves in a control room. It wasn't a guaranteed fix. It was the team's best option, chosen. Because the cost of not trying 3 more months of total blackout on a spacecraft with a shrinking, non-renewable power supply was judged to be the greater risk. On July 31st, 10 days after the antenna mispointed, the Deep Space Network's dish in Canberra, Australia, picked up something. A faint carrier signal, not data, not telemetry, just a heartbeat, the electronic equivalent of a pulse, confirming that Voyager 2 was still transmitting on its expected frequency, still alive out there, still operating, just not pointed toward home. NASA's project team described it as something like a whisper through interstellar plasma, faint but unmistakably there. It meant the spacecraft hadn't failed, hadn't broken down, hadn't been damaged by anything in the 9 days since contact was lost. It had just lost its aim, still fully alive, still fully functional, simply pointed in the wrong direction. That gave the team enough confidence to try something bolder than waiting for October. On August 2nd, the Canberra antenna, part of the Deep Space Network's Australian complex and one of the largest steerable dishes on the planet, sent what NASA's own communications described as an interstellar shout, a high-power S-band transmission, reported at roughly 100 kilowatts, aimed directly at where Voyager 2's antenna should have been, engineered to be strong enough to be picked up by the spacecraft's receiver, even though that receiver was pointed 2 degrees away from Earth. The command instructed Voyager 2 to reorient itself and turn its dish back toward home. Then the team did the only thing they could do. They waited. With an 18 5-hour one-way light time, it would take 37 hours total just to find out whether the command had even reached the spacecraft, let alone whether it worked. Nobody at JPL would know if this gamble had paid off until nearly a day and a half later. For comparison, a round-trip radio conversation with the Mars rovers, already famous for their communication delay, takes somewhere between 6 and 40 minutes. Talking to Voyager 2 in the summer of 2023 took nearly 60 times longer than that, one full sentence sent, and then more than a day and a half of silence before anyone on Earth could hear whether it had landed. 37 hours is a long time to not know if you've just lost one of the 2 farthest traveling objects humanity has ever built. At 12:29 a.m. Eastern Time on August 4th, the wait ended. Voyager 2 began returning science and telemetry data again. It was healthy. It had corrected its orientation. It remained exactly on its expected trajectory, still moving outward through interstellar space at more than 34,000 miles an hour, as if the previous 2 weeks had simply been a pause rather than a near catastrophe. It's also worth understanding what was actually at stake scientifically during those 9 days of silence, beyond the spacecraft's own survival. Voyager 2's instruments, its magnetometer, and its plasma wave subsystem in particular, don't stop working just because the antenna is mispointed. They kept running the entire time, kept sampling the magnetic field and plasma density of interstellar space exactly as they always do. The problem is that data has to be stored on board and then transmitted back to Earth to mean anything at all, and Voyager's onboard memory for this kind of continuous readout is limited. Every day the antenna stayed mispointed was a day of unique, unrepeatable interstellar measurements that risked being overwritten or simply never making it home. Data describing a region of space that, again, no other spacecraft is currently positioned to sample. It's not that the crisis threatened some future observation. It threatened observations that were happening in that exact moment, unrepeatable, and until August 4th, unrecoverable. Voyager project scientist Linda Spilker put it plainly afterward. The fact that Voyager 2 was still sending back a signal at all was, in her words, a genuinely good feeling for the entire team, because it meant everything the spacecraft was supposed to be doing, it was still doing. It just wasn't pointing at us. NASA's engineers even calculated the geometry of the miss. At 12 billion miles away, a 2-degree offset stretches into a triangle so long and thin that the resulting gap is comparable to the distance between Earth and Jupiter. That's the scale of precision required to keep a 1970s spacecraft talking to us across the width of the solar system. 2 degrees, at that distance, is the difference between contact and total silence for months. It's worth pausing here because stories about spacecraft going silent tend to get exaggerated online, turned into something about mysterious signals or unexplained anomalies. This one doesn't need any of that. Nothing about Voyager 2's blackout involved anything unexplained. NASA published the cause, the timeline, and the fix in real time through its own Jet Propulsion Laboratory updates. And every detail here traces back to those official mission logs. The reason this story is worth telling isn't mystery. It's math. A 46-year-old spacecraft, a 2-degree pointing error, a 9-day gap before any signal was detected, and a 37-hour wait to learn if a single high-power command had worked. Every number in that sentence is real, documented, dated, and traceable back to NASA's own public updates from the Jet Propulsion Laboratory. And every one of those numbers is exactly what actually made this dangerous. So that's the crisis. A software update, a 2-degree error, a 9-day gap before any signal was heard, and a 37-hour gamble on a single high-powered command that had never been tried in quite that way before. It worked. But here's the part most retellings of this story leave out, and it's the part that actually matters most. What happened after Voyager 2 came back online, and what scientists have since found buried in the data that spacecraft and its twin have continued to send home. Because the return of signal wasn't the end of the story, it was the beginning of a much longer one about just how much Voyager data is still rewriting planetary science decades after those flybys happened. And this is where it gets genuinely strange, because some of the biggest discoveries tied to Voyager 2 didn't happen in 1986, or in 1989, or even in 2023. They happened in 2025 and 2026, using data the spacecraft had already sent home decades earlier, data nobody had fully understood until now. In February 2026, a team of researchers, including scientists at the Southwest Research Institute, published a study in the journal Geophysical Research Letters that went back through Voyager 2's original 1986 flyby data of Uranus, applying decades of knowledge about how Earth's own radiation belts behave to reinterpret readings that had sat mostly unexplained since the spacecraft first sent them home. What the team found was that Uranus's electron radiation belt appears to have been dramatically intensified, effectively supercharged, at the exact moment Voyager 2 flew through it, driven by magnetospheric conditions the mission team in 1986 simply didn't have the framework to fully interpret. There wasn't a comparison point yet. Nobody had studied another planet's radiation belts closely enough to know what an anomaly even looked like. In other words, nearly 40 years after the flyby, we are still discovering new physics buried inside data Voyager 2 already sent home in the 1980s. The spacecraft did its job in 1986. The science needed to actually understand what it recorded didn't fully exist yet, and in some cases is only catching up now in 2026. That's not an isolated case. Earlier research using this same Uranus dataset helped explain a mystery that stood for decades. Why the planet seemed to have essentially no internal heat of its own, unlike every other giant planet in the solar system. New modeling published in 2025 showed Uranus actually does emit more energy than it receives from the sun, just far more subtly than researchers had been able to detect before, resolving one of the strangest anomalies in the Voyager 2 archive. And in August 2025, astronomers using the James Webb Space Telescope found something Voyager 2 never could have. A new, tiny moon of Uranus, only about 6 miles across, so small it went completely undetected during the 1986 flyby, and only came to light thanks to infrared instruments that didn't exist yet when Voyager passed by. Uranus now has 29 known moons. Voyager 2 is still indirectly guiding where we look. This is really the heart of why the July 2023 blackout mattered so much. Voyager 2 isn't just a historical artifact. It is an active scientific instrument, one of only 2 spacecraft ever to sample the plasma and magnetic field conditions of true interstellar space directly, with the other being its twin, Voyager 1. Every additional year of data these 2 spacecraft send back is priceless, because building a replacement isn't something you can do quickly. There is no other mission currently in that region of space, and there won't be another one there for decades, at minimum. Losing Voyager 2 in 2023, even for the 3 months it would have taken to wait for the automatic reset, would have meant losing months of irreplaceable interstellar plasma readings during a period when both engineers and scientists were already racing against a much bigger, slower problem: power. Both Voyager spacecraft run on radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium-238 into electricity, with no moving parts to wear out and nothing to refuel. That's exactly why they've lasted this long. But the physics of radioactive decay doesn't negotiate. The plutonium's heat output drops on a fixed schedule, and with it, so does the spacecraft's usable power, by roughly 4 watts every year, permanently and irreversibly. There is no upgrade path. There's no swapping in a fresh battery 12 billion miles from the nearest hardware store, and there never will be, not on any timescale that matters for this mission. Whatever power is left when you finish watching this is genuinely all there will ever be. NASA's engineering teams have spent the last several years carefully rationing what's left, turning off individual instruments one at a time to keep the most scientifically valuable ones running as long as possible. Voyager 1's low-energy charged particle instrument is expected to be switched off by the end of 2025. Voyager 2's cosmic ray subsystem is scheduled for shutdown in 2026. According to NASA's Power Conservation Plan, published in 2025, these trade-offs are designed to keep at least one science instrument running on each spacecraft into the 2030s, more than half a century after launch. But the same report is candid that the Voyagers have already weathered nearly 50 years in deep space, and unforeseen problems, like the one in July 2023, could shorten that runway further. Which is exactly why the antenna incident wasn't just a scary week for the mission team, it was a preview of the kind of failure that could actually end the mission early. Not through power loss on a predictable schedule, but through a single small error compounding at a distance where nothing can be fixed quickly and nothing can be verified for days. A 2-degree mistake at 12 billion miles came within one bold engineering decision of costing us 3 months of contact with a spacecraft that has a shrinking, non-renewable power budget and no possible replacement. As of now, both Voyager spacecraft remain healthy and are still returning data. Voyager 1 is more than 15 billion miles from Earth, and on its current trajectory, NASA calculates it will become the first human-made object in history to reach a distance of 1 full light day from Earth, more than 16 billion miles, on November 18, 2026. That's a distance so large that light itself, the fastest thing in the universe, needs a full 24 hours to cross it. Voyager 2, meanwhile, continues to operate its magnetic field and plasma wave instruments. the exact instruments responsible for helping scientists understand the structure of the heliopause and the true shape of the boundary between our solar system and the rest of the galaxy. Every week that passes without another communication failure is another week of data from a region of space that, right now, only these two aging machines can reach, and that no mission currently being built is positioned to reach again anytime soon. So what actually changed once Voyager 2 came back online in August 2023? Not a discovery in the sense of some singular headline moment. What changed is quieter and, honestly, more significant than that. It became clear just how fragile this mission's remaining lifetime really is, and just how much science is still waiting to be extracted from data. These spacecraft have already sent, and will keep sending, as long as nothing else goes wrong. The 2026 Uranus radiation belt paper, the resolved heat emission mystery, the newly found moon guided by old flyby geometry, none of that would exist if that August 2nd command hadn't worked. All of that is downstream of one high-power signal sent across 3 billion miles, arriving just in time. There's something worth sitting within that. Two of the most consequential machines humans have ever built are currently flying through a region of space no other spacecraft will reach for decades, running on power sources that cannot be refueled, communicating across a gap so vast that a single conversation, command sent, response received, takes the better part of 2 days. And in July 2023, all of that nearly ended not because of some dramatic system failure, but because of an ordinary command, a 2-degree mistake, and 18.5 hours of silence stretched out over 2.5 weeks. It didn't end there. NASA's team found the heartbeat. They took the gamble. The shout worked. And because it worked, we're still learning things Voyager 2 recorded 40 years ago, using tools that didn't exist when it flew past Uranus, still resolving mysteries about a planet that's more than one, 7 billion miles away. And still, right now, gathering plasma and magnetic field data from true interstellar space that nothing else humanity has built can currently collect. The real story here isn't that Voyager 2 went silent and came back. It's that it almost didn't, and that everything we've learned since is time we very nearly didn't get. 2 spacecraft, launched in 1977, still flying, still listening, still teaching us things about our own solar system that we didn't know. And somewhere out past the edge of the sun's reach, both of them are still moving outward into a version of space human eyes have never seen directly, sending back a signal that takes almost a full day to arrive, for as long as their power holds out. What happens when the last instrument finally goes quiet, sometime in the 2030s, is a question nobody can answer yet. NASA's own engineers have said as much. The current power plan is built to stretch at least one working instrument on each spacecraft into that decade. But they're candid that 47, now approaching 50, years in deep space brings risks no model can fully predict. July 2023 was a preview of exactly that kind of risk. A single ordinary mistake nearly costing months of irreplaceable contact with a spacecraft that cannot be repaired, cannot be refueled, and cannot be replaced on any realistic timeline. But for now, both Voyagers are still out there, still transmitting, still rewriting what we thought we knew about a solar system most people assume we've already finished mapping. Somewhere past the edge of the sun's influence, 2 machines built before the personal computer existed are still sending back a faint, real signal from a place nothing else has reached. A signal that takes the better part of a day just to arrive, for as long as their power holds out. And after what happened in July 2023, after 9 days of not knowing, a faint heartbeat picked up in Canberra and one 37-hour gamble that could have gone the other way, that alone is worth paying attention to. 2 spacecraft, built with technology from before most of us were born, still working, still transmitting, still teaching us things about our own solar system that we didn't know, because the next time Voyager 2 goes quiet, there may not be a second shout left to send, and there may not be a next spacecraft ready to take its place for a very long time after that.